chose the point C so that the two unknowns, FCX and FCY, didn't show up in this equation. Let's say we had decided to write the sum of the moments around the point B. Or actually, let's say we wrote the sum of the moments around the point D. That'd be really unwise because now we get all three of these unknowns showing up in that equation. So it makes it a little bit harder to solve the three equations for the three unknowns. So when you're looking for a point to write the sum of the moments around, see if you can find a point where some of your unknowns are at. Maybe choose that point. I can't say that's always the easiest place or always the best place to go, but oftentimes it is. It's a good place to at least try first. All right, let's see. We'll practice a few more. All right, let's go up to 4.29. Okay, so here once again we have some rigid body, this L shape. Again, you see there's a pin that's helping support that rigid body at the point C. There is also this rope which starts at the point A, goes up and around the pulley at B, and then back down to the rigid body at D. Somebody's grabbing the corner of this rigid body. Let's just give that point a name. It's not labeled in the book, but just so that we have a name to give it, let's call it E. So somebody's grabbing the corner E, and they're pulling straight down with a force of 150 newtons. So we can call that force Fe now. So our job is to find the tension in the cable. And find the reaction force at C. Sometimes it'll just say reaction instead of reaction force, but when you see reaction, you have to know that means reaction force, which means you're going to have a vector answer there. So we have to find the tension in the cable, so that's just going to be a scalar result. We're just looking for the magnitude of the tension there. But then the reaction force at C is going to be a vector result. So let's see what happens here. So somebody grabs the corner E and they start pulling down. Well, if that were the only thing we would get some rotation around the point C. But this rope is constructed in such a way that it's going to kind of oppose whatever wants to happen when we pull down on E, so the net result, everything will stay still. So we're in equilibrium, which means our equilibrium equations are going to hold true. So we can write the three equilibrium equations that we can for two-dimension problems. That would be sum of the forces in the x direction equal to 0, sum of forces in y, and then the sum of the moments around any point equal to 0. So let's take the sum of the forces in the x direction. Now maybe before we start writing the equation, we should draw the free body diagram so that we know what all the forces are that we're dealing with. So of course I got Fe, which is the 150 newtons coming straight down on the corner here. I've got that frictionless pin at the point C. We saw that before. It's a pretty common support structure, so we're going to have the same thing that we saw before, where there might be an x component, Fcx, and a y component, Fcy. And then, of course, the rope can exert a force on the rigid body. And it's going to exert that force in two different places, at A and at D. In both places, it has to pull. Okay, in both places, it has to pull. So you're going to have a force on A that's heading up in this direction. You're going to have a force on D that's pulling up in this direction. Now, it's the same rope, so it's got to have the same tension. So I'm going to use the same letter T to represent the force at A and at D. Okay, one rope can only have one tension in it, no matter how it's wrapped around pulleys. Now here's an important point to make it at this time. This pulley B is attached to some external wall. External meaning it's not a part of this rigid body. Okay, it's some separate structure. That's what allows us to write this tension in both of these places like this. If the rope didn't pass around this pulley, let's just say you had a rope that went straight from A to D, that rope is not connected to any external body. There's no external force there. You wouldn't be showing it in your free body diagram. You could, but what would you have? You would have a tension this way, a tension equal magnitude this way, so you have two tensions, equal magnitude, opposite direction, same line of action. In every sense, they cancel out.
Yes.
Okay? They, same magnitude, opposite direction, so they cancel out that way. And because they have the same line of action, if you take it's a force couple, if you take the moment of that couple, the magnitude of the force is t, but the distance between their lines of action is 0, so there's no moment. So you can put them, t and t, but in all of your equations, they're going to end up canceling each other out. So when we draw the free body diagram, we're really only interested in looking at external forces. And this tension becomes an external force because the pulley is attached to an external support structure. Okay, so if you have structures where, let's say, a rope directly connected one point of the rigid body to another, no need to show it in the free body diagram, no need to put it in the equations. Those two will always end up canceling each other out. But when it's around an external body, then we have to consider it. Because now you can see this obviously is not going to cancel this. And then I suppose the only other thing we might put here is there's going to be some angle associated with that tension. We don't really have angles, but we do have some dimensions that we can use to make this kind of reference triangle. So coming across the horizontal is 300 millimeters. And then up the vertical from A to B is 125. So your rise over run for that tension, you have 125 on the rise and 300 on the run. If you need the hypotenuse of that reference triangle, just do a little Pythagorean theorem and you get 325. All right, so now we should be able to start writing the equations. So for the x direction, let's say we have this tension at A, which will have some component in the x direction. It's going to be the tension times the cosine of the angle that we have right here. Well, the cosine of that angle, I don't know the actual angle, but I know the cosine is the adjacent over the hypotenuse, so it's going to be 300 over 325. If want to figure out the angle and then put t times the cosine of whatever number of degrees it happens to be, fine. But we don't need to. We can just write cosine as adjacent over hypotenuse. So that takes care of this one. Now, of course, FE, vertical, no component shows up in the x equation. Same thing, FCY is vertical, but FCX is horizontal, so I'm going to put plus FCX. And then the tension at D is vertical, so nothing else shows up there. So I can set this one equal to 0. Well, those are both unknowns. So I really can't do anything with this equation as it stands right now. So let's write some of the other equations. Fy, sum of the forces in the y direction. So the tension at A is also going to have a vertical component. This time it'll be the tension times the sine of the angle, opposite over hypotenuse, 125 over 325, minus Fe, because that goes straight down, plus Fcy, plus T, equal to 0. Well, just like before, we wrote a second equation, but we introduced the third unknown. So 2 equations, 3 unknowns. Can't solve that system yet. We need to write the third equation. The third equation, sum of the moments around any point. Now, if we choose our point wisely, just like before, we can make our life easy when it comes time to solve the 3 equations. If we choose a point unwisely, we can still solve the system. It'll just take a lot more work and be a lot more tedious. So my suggestion was, if there's a point where some of your unknown forces are acting, choose that point. Well, C, 2 of the unknown forces are acting there. So let's choose the point C again. By doing that, I know those 2 unknowns won't show up in the equation. So at this point, we should have one equation with 1 unknown. We can start to unlock the system that way. All right, so sum of the moments around the point C. Now, the tension that's acting up at the point A, don't forget, that one has 2 components. That's got a horizontal component. That also has a vertical component. Each one of those components is going to create a moment around C. Because if I hold the point C fixed, and I push to the right on the point A, it will generate clockwise rotation. If I hold the point C fixed and I push up on the point A or pull up on the point A, that's also going to create clockwise rotation. So each one of those components wants to create a negative moment around the point C. So what do we have here? Negative, because it's going to be clockwise, and if we do the x component first, we'll have the magnitude of the x component. That's t times 300 over 325. And it's the same x component that we just saw right here, times the distance between the x component's line of action and the point C. So the x component's line of action is here. The point C is down here, 175. If you want, you can put that in terms of meters and make it 0.175. Okay. But I'll leave it in millimeters this time. We said the vertical component also has a negative moment around the point C. This time it's going to be t times the sine, which was 125 over 325. So there's the magnitude of our vertical component. So that should match up exactly with what we see here. But now the distance between the vertical line of action, so here's the vertical line of action and the point C, that's our 225. So the tension that's acting at the point A, we kind of have to break it down into its x and its y components. Maybe there's a way, based on the dimensions in the figure, to figure out the perpendicular distance from that line of action to the point C. Okay? So if you had some perpendicular line like this, right, because that's the line of action for that tension right there. So if you drew a perpendicular line from that line of action down to the point C, if you could use the dimensions in the figure and figure out that distance, you could just take t times that distance. But I don't know, at first glance it looks like it might be a little bit difficult to find the distance of that perpendicular line. So I just split this into x and y components because I have those dimensions already given to me. All right, let's see what's next. Okay, this force at E. So if we hold the point C fixed and we pull down on the point E, that'll spin us clockwise around the point C. So this one's going to end up being a plus. FE, and then the distance, it's the same 225 that we had already because it's that same vertical line of action over to the point C is 225. Now the forces at C, because their lines of action go through C, there's no moment. Okay, it's whatever that magnitude is times 0, so there's no need to show it in the equation. The tension at D will also create a moment at C. Now if we hold the point C fixed and we pull up on the point D, that's going to spin us counterclockwise, so it's another plus. The tension times the distance from this line of action to the point C, you can read it off the figure, 75 millimeters. That's equal to 0. So FE, we know that value. That's the 150 that was given. So you can drop that one in here. And now the only unknown left in the equation is T. Little bit of algebra involved because you've got to combine the three like terms here before you can solve for T, but that's not a big deal. Do that algebra, you should get T is equal to 195 newtons. So now that T is equal to 195, we can come back and drop that number in right here, 195. 195, and solve for FCX and FCY. Remember, FE was 150, so we know that one in the Y equation. Okay, we also drop in right here, 195. Now here's sort of a thing to keep in mind. Remember, tensions can only pull. So we have to show their directions correctly in the free body diagram as a pull. So if we know that we're showing the direction correctly for these tensions, we should always get a positive result. If you solve this equation over here and you get minus something, then you messed up somewhere. You should be getting positive 195. Did anybody else solve it out? Verify that's right. Positive 195. So remember, this one is 150 right here. So let's see. If we take 300 over 325 times 175, that's 161.5. So what do we end up with here? So minus 161.5 T over here, 125 divided by 325 times 225, 86.5 T. This one should be 150 times 225, which is 33,750. And then this one plus 75t equal to 0. So let's take all of the t's and move them to the other side. So this will be a plus, and a minus. So 161.5 plus 86.5 minus 75. So you get 33750 equal to positive 173t. Right, because your 161.5 plus 86, that's going to give you something around 250, and then you're subtracting off your 75. Why isn't the 150 negative? Okay, because that's a good question. So if FE is going down, If FE is going down, why are we plugging in positive 150 right here? That's the question. Well, we took the fact that this is moving down when we checked the direction of the rotation. Okay? So we checked the direction of the rotation and we got a counterclockwise rotation. So I got the plus right here. Okay? That plus took into account that this was acting down. So if you then put the minus sign in for the 150 and put negative 150 here, then it's like you're getting a double negative because you're accounting for the direction once with the rotation, but then you're putting in the minus sign again. So that double negative is what's going to throw you off. Okay? So remember, when we do this F times D technique, we're plugging in the magnitude of the force. The magnitude of the force doesn't rely on the direction. Okay, so it's 150 newtons magnitude. That's what's getting plugged in. The direction, the fact that this is down, is accounted for with the plus sign. Okay. So then you divide this, that gives you the 195. When you drop into the x and the y equations, let's see, did anybody get Fx and Fy for the reaction force at C?
Professor.
Yeah.
What if first we trying to find the tension and trying to find the angle for the A right there? So we can say substitute sum of force C is equal to 0, so we can do sine and cosine to solve for the tension.
Wait, hold on. So you're talking about this up here at point A?
Yeah.
Okay, so what about this one?
We find the angle.
You can find the angle just using the dimensions of this triangle. Right, just do inverse tangent of 125 over 300. That'll give you the angle in terms of degrees. You're talking, why don't we have an angle down here?
Yeah.
It just asked us to find the magnitude. It just said find the tension in the cable. That means the magnitude of the force that's in the cable. Because it shows up in two different places, you would really have two different directions associated with it. You could say the tension at A, and write that in vector form. So you could say, they didn't ask us to do this, but you could say the tension at A is equal to 195 newtons. And then you figure out that angle, like you said. You could use like an inverse tangent. And then the tension at D would be 195 newtons going straight up. So if they asked you to find the tension vectors at those points, you could do that now. Okay? But they just wanted the tension in the cable. The directions are kind of obvious from the figure. Okay, so that's why they didn't really request that we go that far. But how about FCX? Did we solve for that one?
Negative 180.
Negative 180? And FCY?
Negative 120. 120.
Negative 120? Okay. Now, just like we did before, you're going to want to take these two results and find your magnitude. So negative 180 squared plus negative 120 squared. And find your angle, inverse tangent, of negative 120 over negative 180. And express this in magnitude and direction form. So let's see, what do we get? What's the magnitude?
216.33.
Okay, so we'll call it 216.3. And if we take the inverse tangent,
33.69.
okay, so we'll call 33.7 degrees. So I say here the force at C is 216.3 newtons. Now, again, negative and negative, the force is actually into the third quadrant, 33.7 degrees. So same exact process that we did with the previous one. It's just applying those three equations, the three equilibrium equations for the rigid body to a different figure.
Why is it in the third quadrant?
Why is it in the third quadrant? Because the x component and the y component are negative.
Oh, okay.
So you're pointing to the left and you're pointing down.